Yes.
Cool. Can we get started?
Sounds good.
Excellent.
Yep.
All right. Welcome back, everyone. So, the next speaker for today is going to be Sewon Min. Sewon is an incoming professor here at Berkeley. She's done a lot of exciting work, both in sort of understanding phenomena in current language models, so things like in-context learning, and also kind of augmenting current architecture. So today she's going to tell us a little bit about retrieval-based language models. Let's all welcome Sewon. And Sewon, please take it away.
Okay, thanks for the introduction. Hi, everyone. Thanks for coming. And I'm sorry for not being able to be there in person. I'm kind of sad to be remote, but I'm still very excited to have the opportunity to present at the workshop and share some of my work in retrieval-based language models. So before I start, I must mention that technically the content of this talk is not about transformers as a building block, but in fact, this is closer to a general approach that could potentially work with any kind of building blocks. But for the models that I will be presenting, we happen to use transformers as a building block because it happened to be the state-of-the-art model. So my talk wouldn't specifically focus on building blocks, but I think you can consider it as a way of alternative architecture that is not a single dense parametric model, unlike other transformer-based models that we see nowadays, but rather it's a different kind of architecture that you can build while using transformers as building blocks, or potentially with other kind of building blocks. Okay, so let me get started. So we all know that today's large language models are created by collecting a large text corpus from the web consisting of trillions of tokens and learn a massive number of parameters on this data. So for every training instance, we train the model using the next token prediction objective. And then once training is completed, the data is discarded. And we use these learned parameters to make a prediction for every test input. This works surprisingly well in practice because parameters can remember many pieces of information from the training data that are relevant to the test input. But at the same time, this is also a restriction. The model works only when parameters can remember relevant details from the training data. But this could lead to various problems. For instance, building such a model is very costly because you need a massive number of parameters to make it work. And even then, the model may still fail to remember details from the data, and it leads to generation that contain incorrect facts. And finally, the model remains strictly inflexible and still once training is completed. It's very difficult to update the model after training is done. So a retrieval-based language model refers to a model class that include not only learned parameters, but also a data that you can keep instead of discarding after training. So here, for every test input, the model should be able to locate relevant pieces from the data and reason over them to make a prediction. And now you can see that we no longer need to remember every detail from the training data because we can always look it up at test time. So we call this test time data or data store to distinguish from the training data. And importantly, this data store is flexible and can change at any time. That means now the model can grow by expanding the data store or be seamlessly updated by keeping the data store up to date. For instance, by adding breaking news to the data store. And this is without any additional training. This is unlike existing models that are very difficult to update after training. Okay, so that was a brief motivation for retrieval-based models, but how can we build such a model? The most straightforward approach is to use a two-stage pipeline, which is also often called RAG or retrieval augmentation. Given a data store and a test input, we first use a retrieval system to retrieve a set of documents or passages from the data store that are most relevant to the test input. And then we feed them into the language model to reason over them and make a prediction. So this idea has existed for a long time, but in context of large language models, the community has modernized this approach across different parts of the pipeline. For instance, one of the components that we had significant improvement in a few years ago is on retrieval part. For instance, one of my work called dense passage retrieval was propose a new way of training the neural encoder, which is the essential part of retrieval model. And this actually has been one of the work that popularized retrieval augmentation in the context of large language models. But I would say that improvement in passage retrieval mainly came in 2020 and 2021. And more recently, the advances has mainly came from language model training in general or scaling various part of retrieval-based model, like retrieval model or a data store. So in today's talk, I will mainly focus on these recent advances. In particular, I'll talk about two recent work that I have worked with. In the first part of the talk, I will talk about pre-training the language model with retrieval, which focuses on the second stage of the pipeline. In particular, our work is in fact one of the first work that pre-trained the model from scratch using retrieval. And I'll talk about how exactly we can do this. In the second part of the talk, I will talk about scaling a retrieval data store at the level of pre-training corpora, like trillions of tokens. And we'll talk about how this can open up a new avenue of studying different scaling properties. So that is an overview, and let me get started with the first part, pre-training with retrieval. This is a project led by my collaborator, Wei Jiaxin. So as I briefly mentioned earlier, the two-stage pipeline first retrieve a set of documents from the data store, in this case, document 5 and document 3. And then we feed this to the language model and get the prediction. And the simplest way to do this is to concatenate all the documents and query into a single piece of text and feed into the language model that we already have, which is trained in a regular training objective. So intuitively, we concatenate document 5, 3, and query into a single piece of text and feed into the model and get the prediction like this. This works surprisingly well in practice, even though we are not really training the model retrieval. But at the same time, this format is also new to the language model. The model has never seen such a format that is a concatenation of different documents. So the key idea here is, can we pre-train the model to use retrieved context so that it can learn how to make best use of retrieved documents? So the idea is very simple, but how can we actually achieve this? So let's brainstorm together. Suppose you have a large collection of documents as your training data, and one of the document is this document, document 0. And normally, what you do to train the model is simply to feed into the language model and train it with a next token prediction objective. Now, with retrieval, what you will do is to use an off-the-shelf retrieval model to retrieve relevant documents like document 5 and document 3, and then concatenate that with document 0 and feed into the language model. So this part is quite intuitive because that's exactly same as the test time scenario. Now, the open question here is, where do we apply loss to? One option is to apply loss only to document 0, because document 0 is kind of our query document. The problem here is that the training is very inefficient. This is because we're already conditioning on lots of tokens, but the training signal only comes from a single document, which is document 0. So we're not really making use of all the documents that we are using. So the other option is to apply loss to all documents, including document 5, 3, and 0. And now we don't have an inefficiency problem anymore. In fact, this could be even better because it can potentially generalize to varying number of retrieved documents. But there is a new unexpected problem, which is the duplication. So what happens in this scenario is that we have a large collection of documents and data, like document 0, 1, and 2, and then we have retrieved documents for every document. So that's document 5 and 3 for document 0, and then 5 and 9 for document 1, and 7 and 5 for document 2. But then some documents may appear more frequently as the relevant retrieval context for the other. For instance, in this case, document 5 appears so many times. And if we simply train with this objective, then document 5 will be appearing as training data so many times. So it could struggle with duplication problem. So what we really want to do is to avoid this problem by making sure that every document is seen exactly once during training. So how can we do that? So we cast the problem into a document ordering problem as follows. Given a pre-training data consists of many documents like this, we construct a graph of documents where each node is a document, and a node represents whether a pair of documents is related to each other or not according to the off-the-shelf retrieval model. Once we have this graph, we can convert it to a chain of documents by traversing the graph. And then we can group a few documents based on whether these documents are enough to hit the maximum sequence length limit of the transformer that we predefine as a hyperparameter. So in this case, we group 0 and 9, 1, 3, and 5, and then 7. Finally, once we have that, we can concatenate documents within the same bucket into a single piece of text and then run pre-training as it is. So for instance, in this case, we concatenate document 1, 3, and 5 and fit into the language model and apply loss to everything. That part is exactly the same as typical pre-training process. And now you can see that this satisfies all conditions that we need to meet. The model conditions on a set of relevant documents, which exactly simulate what happens at test time with retrieval. And second, each document appears exactly once, so we are avoiding the duplication problem. So we have many results in the paper, but here I will focus on one of the results in factoid open domain question answering. So this is our baseline, that is a regular language model, and we are not using retrieval. And then this is another baseline where we are using retrieval, but the language model is still the standard language model, meaning that it is trained without retrieval in mind. So we can see that even though the model is not trained with retrieval, it's already better than not using retrieval. And then here is a new model that is trained with retrieval, but with document repetition. This model does not work quite well because of the duplication problem that we discussed earlier on. And finally, this is our model that is trained with each document appearing exactly once. We can see this model works much better than all the other baselines, including the baseline that is not using retrieval and baselines that is using retrieval, but with the standard language model. Okay, so that's the key result in the paper. To summarize, we proposed to pre-train the model with retrieval from scratch. We found naive approaches do not work quite well, either because it's not efficient enough or there are duplication problem across documents. So we casted a problem into a document reordering so that each document can be seen exactly once. We see there is more than 10% improvement in downstream tasks with retrieval. And I didn't show the graph, but in the paper, we also have a result where the improvements are larger when retrieval results do not support answering the query. And what I mean here is retrieval could sometimes fail. Maybe the retrieval documents are not relevant to the test query. And in that case, the previous approach could fail in giving a good answer because it could be easily distracted by irrelevant passages. But then in our model, it is more robust to this irrelevant document, likely because the model have trained with them so that it learned how to avoid being distracted by this document. I think this is one of the unexpected benefit by pre-training the model with retrieval. Okay, hopefully this is clear. So that was about pre-training the model with retrieval. Now I will switch gear and move on to the second part, which is about scaling a data store. This is a project led by my collaborator, Rulin Xiao. So one of the reasons I think retrieval-based language models are exciting is because it can potentially provide a new avenue for scaling. What I mean is, previously, there are two main dimensions in scaling, the number of parameters and the size of the training data. However, scaling is very expensive because scaling each of these dimensions requires massive GPU computation, which is expensive. But then in retrieval-based language model, there is a new dimension in scaling, which is the size of the data store. And scaling a data store requires CPUs and storage, which are significantly cheaper than GPUs. This raises a question. Can we build a retrieval-based model that consists of a small model and a large data store, and hopefully match or outperform a large language model? And if that is possible, then this can offer a completely new way of scaling the model with significantly less cost. So we want to study this, but there is one important ingredient that is required to study this, which is a large data store. So what is the scale of data stores used in previous research? So there is a long line of prior work in retrieval-based model, but many of them use English Wikipedia as a data source, and the size is restricted to less than 5 billion tokens. That's tiny compared to the modern pre-training corpora. There are some other work that use pre-training data as data sources, such as Common Crawl and the Pile. However, this work typically subsample the data, so it's still restricted to tens of billions of tokens. We are aware of only one work that scaled the data store to trillions of tokens, which is Retro from DeepMind. It's 2 years ahead of us, so it's incredibly impressive. However, this work has a few problems. The problem is that their data is not deduplicated, and the experiments were done only in Perplexity, and therefore it was not clear whether the performance gains are coming from contamination or not. And unfortunately, their data store is not open source, so we were unable to follow up study. Therefore, we ended up constructing our own data store, which we call Massive DS. It consists of 1.4 trillions of tokens, which match the scale of modern pre-training corpora. We construct the data store from various sources. A large portion of them is coming from Common Crawl, but we also have various other domains such as academic papers, code, books, and math and biomedical corpora. So since now we have a large data store, we can study scaling properties of the model. So first, we look at language modeling perplexity using a range of Bayes language models, including Llama 2 7 billion, 13 billion, and Llama 3 8 billion. And considering their training size, you can assume that as we move on to the right, the more training compute was used. This is a result on perplexity, so the lower the better, and x-axis indicate the size of the data store in terms of the number of tokens. I want to quickly note that the result on Llama 2 and Llama 3 are not comparable in this graph because they use different tokenizers. But we can still compare within the same line. And as you can see, we scale the data store, perplexity goes down, meaning there is consistent improvement in performance. These are the results on 4 downstream datasets, Trivia QA and NQ, which are factoid open domain question answering datasets, MMLU, which is knowledge/reasoning dataset, and MathQA, which is a medical question answering dataset. And here, all models are comparable to each other. And here we can see that again, there is consistent improvement as the data store scales. But then the trend is slightly different depending on the dataset. For instance, for Trivia QA and NQ, we see that there is a significant improvement as the data store grows. And in fact, a small language model plus a data store is significantly better than a larger parametric language model. However, this may not necessarily be the case in other datasets. For instance, if we look at the MMLU data, we see that there is a consistent improvement as the data store scales, but a small language model is not able to match the performance of larger parametric model. In MathQA, there is an interesting trend that the improvement is consistent when we use Llama 2 7 billion. In fact, that can match the performance of Llama 2 13 billion. However, if you use larger parametric model or model that is trained longer, like Llama 3, then the gains by using a larger data store is not very clear. I think part of the reason is because our retrieval model is not good at retrieving medical documents because they were never trained on medical data. But for now, I think we can conclude that although generally there is a general trend that scaling a data store helps, the specific degree of improvement depends on the choice of downstream tasks. Okay, so now here is the more interesting question. I think what we are actually interested in is when we have a fixed budget for compute, what is the best way to use this compute budget? Is it for scaling the number of parameters? Is it for using larger training data? Or is it for scaling a data store? So in order to study this, we use a range of model checkpoints and report the performance. So for instance, we use checkpoints with 1 billion or 7 billion parameters, and then checkpoints trained on varying sizes of data and use it together with data stores with varying sizes. We studied this with almost 1 billion and 7 billion. This is the state-of-the-art model among those where we could find intermediate checkpoints. And these are results over 4 downstream datasets. These graphs look a bit complicated, but let me walk you through it one by one. So you can see there are many pink dots, either darker pink or lighter pink. This means result on different checkpoint with varying number of parameters and varying sizes of data. And the x-axis here is training flops. This includes flops used to train the model and flops used to construct a data store. So we have many dots here. And then now for every fixed budget for compute, we can draw a Pareto optimal line. That means a maximum performance that you can get with the fixed compute budget. So the blue line here means Pareto optimal for regular language model that is not using retrieval. And red line here means Pareto optimal for retrieval-based language model. And you can see that for all datasets and across almost all range of training flops, using retrieval has much better Pareto optimal than not using retrieval. For instance, for trivia, QA, and natural question, the gap between using retrieval and not using retrieval is very significant. And more interestingly, this gap grows as you scale the training flops. Some of you may find this counterintuitive because maybe the gain by using retrieval will diminish as you scale training flops. I think that is not the case because actually the benefit of using retrieval necessitates competitive language model. So your language model has to be good enough to get benefit from retrieval. I think that's why the gap between using retrieval and not using retrieval gets larger as you grow the training flops. If we look at MMLU and MathQA, the gaps are smaller, which is probably for the same reason as we saw smaller gap in the previous slide. But still, retrieval is still almost always better than not using retrieval across all ranges of training flops. Okay, so that's most of the result I have for this project. So let me briefly summarize part 1 and part 2. So in part 1, we look at how we can pre-train the language model from scratch with retrieval. We proposed a way to do this while keeping efficiency and avoid duplication problem. We find that there is large improvement compared to baseline that is not using retrieval or using retrieval with regular base language model. And the improvements are larger when retrieved documents are irrelevant or distracting. In the second part of the talk, I talked about how we can scale a data store to trillions of tokens. That is the scale of modern pre-training corpora. In fact, this is first among open source models. We studied different scaling properties. For instance, we showed that scaling a data store leads to consistent improvement. And compute optimal setup is almost always with retrieval across a range of downstream tasks, although the degree of gains depends on the choice of task. Is it clear? Okay, I think I have about 5 minutes left, and in the remaining time, I want to discuss some of the open-ended questions related to retrieval-based language model that I'm interested in looking at in the future. And what I mean by open-ended really means that we don't have the answer, and there is an equal chance that this is completely failure. For instance, I think something that is not an open-ended question is, does retrieval help tasks requiring factoid knowledge? I think the answer is almost certainly yes. Retrieval is already being used for information-seeking queries by default, including in commercial systems like ChatGPT and BART. But something that is not clear to me is, can retrieval replace training? Does adding a data store and using retrieval on top of them give an impact that is equivalent to, or even better than training on the data? I think this is something that we really don't have answer to. And in order for the answer to this question to be yes, retrieval should help across a range of downstream tasks, not just tasks that require factual knowledge. I think one of such tasks that we care about is reasoning. We know that using larger model and training on more data is very critical for reasoning tasks for whatever reason. But now the question is, can reasoning get benefit from retrieval? In fact, there are a couple of papers that claim that retrieval does not really help reasoning. I think the setup in these papers make a lot of sense. But what's unclear to me is it because we are doing something wrong? Maybe the retrieval model is not suitable for reasoning, or the augmentation method is not good for reasoning. Or is it because retrieval just fundamentally cannot help reasoning? So my hope is that hopefully this is not the fundamental problem and we can solve this issue. For instance, I think one of the bottlenecks may be in a retrieval model because current retrieval model is optimized for semantic similarity, which may not be good enough for reasoning tasks. So can we design a model that can do retrieval beyond semantic similarity? For instance, maybe retrieve documents that have similar logic in reasoning. Another thing that I think we may need an alternative way is to how you do augmentation. So the current way of augmentation, which is to concatenate a set of relevant passages and fit into the model, may be limited. And for instance, it's limited in the number of documents that you can incorporate it to. But maybe for reasoning, you may need a much larger set of documents. And in order to do that, you need a new way of augmentation that can allow incorporation of much larger subset of data store. I think these are some of the open questions that we may need to handle in retrieval-based language modeling. So the second question I'm interested in is, can we use a retrieval approach to build a language model that can respect various data restrictions like copyright? I think this is an important problem that is orthogonal to modeling. For instance, we know that we are using all web data to train the model, but in fact, a lot of web sources are copyrighted or non-permissively licensed. Current language modeling practices largely ignore these restrictions and just train on everything to train a competitive model. But can we build a new model that can respect these restrictions? So one of the proposals we have is to separate permissive and copyrighted data, train parameters on permissive data only, and to use the rest of the data as a data store that we can query only at test time. The idea here is the retrieval has new functionalities such as providing data attribution and supporting opt-out that can mitigate copyright risk. For instance, if the data owners want to get credited for their contribution, then we can give credit back to them because we can trace the attribution back to the data. And if data owners want to opt out from the model, we can support that by modifying the data store without additional training. And hopefully all of this should be achieved while maintaining performance. We have done some initial work on this. I didn't include it in this talk because actually there is another workshop focusing on copyright and watermarking in mid-October. So if you're interested in, please check it out. But in general, I think this is an important avenue and have a lot of interesting modeling questions that we can potentially address with retrieval-based language modeling approaches. So the last question that I think is interesting is, can we generalize a retrieval-based model to include components that are parametric so that we can have a modular language model that consists of a set of components, not just base parametric model and a data store, but also other parametric model so that it looks something like this. I think this kind of modular model have many properties that we liked from retrieval-based model. For instance, this could provide a new way of scaling because you can add more expert or parametric models to the model. You can also add more data or remove more data and also update part of the model by adding, removing, or updating part of the expert. And it could also provide a new way of respecting data restriction like copyright. For instance, we could train some parameters on permissive data and train other parameters on copyrighted data in a way that you can decide whether to opt out this copyrighted data or not, depending on their use cases. So I think these kind of modular language models have new kind of technical questions. For instance, how could you merge different parametric models? How can they communicate with each other, either through natural language or in other way? So I think these are some of the open questions that we can tackle in the future. Okay, that's it. I have. Thank you for staying with me, and I'm happy to take questions.
Questions for Sewon? I have one. So go for it. No, go, please.
So you talked about like copyright and opt-out and stuff. So like in the United States, there isn't like any legal requirement to, or there's no legal weight behind like opt-out abilities. It's like a nice to have thing. How are you thinking about like there's a lot of different ways that you can think about whether required or not, like legally, the respecting wishes of the people described in or who created the data. Like how are you thinking about that? Is opt-out like a example in your mind, or is it something that you're kind of particularly attached to?
Oh, I see. So is the question more about, are there like particular like legal aspect, like specific laws that we're thinking of when it comes to opt-out?
I mean, like there isn't a law that says you need to provide opt-out when training a language model on or
I
like
see.
a
I see.
providing an opt-out mechanism is independent of the question of whether it's legal to train
I
data
see.
models on data without the copyright owners. I was just wondering if like that was a use case that you were like specifically invested in the solution for, or if it was like more of an example.
Right, right. Yeah, that's a great question. I think, well, it is an example, but I think it's actually one of the core functions that we need. So the legal decision is separate because I think we don't know what the legal decision would be about when it comes to training on copyrighted data. I think that remains to be the open question. But in the end, legal is a practical uh space. So I think what's really important is can we provide a practical solution that can mitigate this copyright? And I think one way to do this is can you remove copyrighted data when requested, even after training is completed? I think that's likely to be some of the functions that we will practically need.
Questions for Sewon? I have one. So I somehow find it very curious in the retrieval part that when you sort of retrieve irrelevant or incorrect documents, the performance seems to improve more. Like somehow shouldn't this confuse the model because you're giving it like, extra things to condition on that are kind of irrelevant for the query? Do you have any intuition, I guess, why this happens?
Right, that's a great question. Actually, I need to clarify what I mean by this line where we have larger improvement when relevant retrieved documents are irrelevant. That means compared to the baselines. So here the scenario is fixed. The scenario is fixed in a way that retrieved documents are irrelevant because there was a retrieval failure. And then if within this scenario, if we compare the baselines that are you using the model that is just the regular model and then then our model is better. So, hopefully, I think that clarifies the setup. And then I think the reason this helps in our model is the model was trained with this retrieval. And what I mean is during pre-training, it probably have seen many cases where retrieval has failed, so the conditioning documents are irrelevant. So the model probably has learned how to be robust against them. Whereas in regular language model, the model haven't really seen such a scenario.
And the retriever is somehow in this scenario never fine-tuned. Like the retriever is fixed. It's just that the pre-trained model gets like kind of training with these like concatenations. Right.
Yes, so we are assuming an off-the-shelf model. We are using Contriver, which is a pre-trained language model. But actually, I think we could also do some sort of iterative training where we train retrieval while freezing language model and do the other way around. So joint training is also possible, and there are a few papers about it, but that's very difficult in terms of engineering.
In that case, let's thanks Sewon one more time.
Yes. Thanks for staying with me.
Sewon. All right, we have a 15-minute, I guess,